Now, just a recap. We are looking at the analysis. The behavior of a sequential circuit is actually defined or determined by the inputs, outputs, and the states of the flip-flop. The states of the flip-flop are the ones that give it memory. And you can describe the behavior of a sequential circuit with a state table or a state diagram. We briefly looked at how those ones look like. So the output and next state are functions of the inputs and present state. So when you are told to analyze a sequential circuit, what do they want? They will give you a circuit diagram or a black box, and then you need to develop a state table, a state diagram, sometimes a timing diagram, and identify the circuit. Sometimes you might need to go further and tell the people the problems with the design circuit. That is why we've got things like races and hazards. We'll look at them later, but they are more in asynchronous circuits. We saw that yesterday. We are doing the opposite. Analysis, there is a circuit diagram. You look at the input equations and you work back and describe what the circuit is doing and the problems. Of course, you will look at the state diagram or the state table to do that. And if you don't understand anything, just stop me and ask. So there are steps for analyzing a sequential circuit. First of all, you must identify and label the inputs, outputs, and internal states. Then you determine the flip-flop input and output equation. Then you derive the state equation of each flip-flop. State equation is an equation of the next state as a function of the present and input. Then you construct the next state and output tables. Then you complete to get a state table. We say the objective is to get the step table, which is step 5, and state diagram, which is step 6, and then you identify the circuit if possible. So now we will start with the first most basic example. You've got that circuit. You've been told what does it do? Analyze it. So the first stage we said you identify and label the inputs, outputs, and internal states. Let's be together and get this done. The input is here is X. The output is clearly Y here. Now look at the state variable. The state is the output, the Q output of the flip-flop. We've named it AT. At the current time is the present state. So the state variable is stored by the flip-flop. It's the one that brings memory. So that is one state variable. The present state variable is AT. The present one is at the output of the flip-flop. The next one is in the next clock cycle. The next state variable is AT plus 1. The next one will be determined by what will be at this point D. So the input we've said is X and the output we've said it is Y. So we have labeled inputs, outputs, and internal states. Input is easy, output is easy. Just know that the state variable is the output of the flip-flop. That is where the memory is. Now, the next thing is you determine the flip-flop input. Sometimes it's called the excitation equations and output equation. So the flip-flop input equation is D and the output equation is Y. Can you give me the equation for D as a function of X and AT and give me an equation of Y as a function of the input and present state? Quickly, just do that. The good thing is that at varsity, I'm not really seeing what you are doing. I will not force you to do it, but I know why I'm saying you do it. It's the exam that will force you to do it, and it might be late. So you need a lot of discipline. Online learning is discipline. There's nobody who is monitoring you there. You could be in bed, you could be in a shower, nobody monitors. But what determines is the output. Will you pass or not? So just pay attention, follow what we are saying. We don't like emails at the end of, oh, what I'm in this trouble and all that. Nobody is watching you. So self-discipline. Can you determine the output equation, and the flip-flop input D equation as a function of the input and present state. You should have done that. It's very basic. Anybody who has a problem with doing that? Okay. If you have anything, you can send a chat and all that. I will answer to it. So those ones who did it, the input equation is a function of the present state and input. The input D is, you've got A is being fed back here, or X. The output equation is X exclusive or AT. Okay, now let's move on. We want to derive the state equation, the next state, as a function of the input. A state equation specifies the next state as a function of the present state and input. But for a D flip-flop, we found that D is that. If you look at the D flip-flop, the next state is basically what is at D. So what are we saying? AT plus 1 is just D, which is that. The output here is just what is at D. The logic that is at D is transparent, is seen at the output at the clock edge. So for a D flip-flop, AT plus 1 equals D, which is that. Yes? For the input equation. Okay, Umeshan? It is, or is a plus. Oh, sorry, or is a plus. Umeshan, are we okay? Umeshan? Okay, thanks. That is why what you are saying is right. This is AT, for D is AT or X. That is why we have that plus. And we say the next state AT plus 1 is D, which is given by that for a D flip-flop. So that is that. That is what we call our state equation. You've got the next state as a function of the present state and input. No, we construct the next state and output tables. So those are our equations. From those equations, we construct the next state, the tables. Okay, the question is, what type of machine is that? If you look at that equation, what type of machine is that? The output is a function of what? The present state and input. So it is what type of machine? Somebody to quickly tell me. Okay, check that on your own. The next state table, this, you've got the present state, you've got the input and next state, and you get it from this. You fill in different 0, 1, 0, 1, different combinations, 0, 0, 1, 1. So if AT is 0, X is 0, this is 0 or 0, the next state will be 0. So you fill in the next state. Yes? Yes? People have answered that is a milli machine because the output is a function of the present state and input. It's a milli machine. That is quite good. Okay, now that is the next state table. Now we go to the output table. Same. You fill in 0, 1, 0, 1, 0, 0, 1, 1. Then you look at the output. 0 exclusive or 0 is 0. 0 exclusive or 1 is 1. Like that. You fill in that. So you've got the next state table and output table. The next step is you combine them to form a complete state table. It has the next state and output. So you've got that, you've got that. So you combine them to form that. That is what we call a state table. You've got the present state, input, next state, and output. That output is just that. The next state is just that for input and output. You don't need two tables, you combine them into that. There are different forms of state tables, different configurations, but they all have the same information. Now, next, if asked, remember the state table and the diagram have the same information. Now, we've derived our state table. Can we now draw the state diagram on your own? Just draw the state diagram to understand what we are doing. We were given a circuit. We have the state table. We are saying if the present state is 0 and the input is 0, the next state will be 0. The output will be what? 0. So can we, this and the state diagram are the same. Can we draw the state diagram on your own there? Okay. The 2 minutes are over. Is there anyone who has a problem with drawing it? Hello? Anybody who has a problem? Okay, I will assume everything is okay. You've got, okay, there's some chat there. Okay, okay, now, from what we did yesterday, you've got two states. So you'll have two circles, one with a 0 and another one with a 1. Those are your two states. The state can either be 0 or 1. And you look at them as the present state. So the transition is an arrow. From 0, you go around, come back to 0. When the input is 0 and the output is what? 0. 0, you are here. These are your two states, 0 and 1. You are here at 0. Let's look at this first row. From 0, the next state is what? 0. So the transition will be from 0 to 0. Somebody said it's a milli machine. So you will move from 0 to 0 if the input is 0 and the output is what? 0. So that is why we have that. You move from 0 to 1. 0, you go to 1. That is the movement, the transition. Okay. The input is 1. The input is 1. The output is what? 1. That is that transition. This one here, you move from 1 to 1 with an input 0, output 1. 1 to 1. That one with an input 0, output 1. This is 1 to 1. Input 1, output is what? 0. 1, you move back to 1. Input there, 1. Output there, 0. That is how the transition state diagram is. Now, those two things have the same information. It's just same information presented in a different way. Mathematicians prefer using a transition diagram. When the finite state machines, they prefer this. Some people would prefer this. Machines prefer tables. Now, each of those is better to interpret one to the other. On your own, I'm looking at thinkers here. Some of you have already given up. You're just there to push, work, get a 50, get a job. You shouldn't be that low. You need to aim for something, understand this science. So now, I'm asking for the people who want to think further. The aim is you need to look at this and tell somebody how that circuit behaves. That is the aim. You are given a circuit. You need to tell somebody. That somebody is a manager who has not done electronics or what, but he knows some big names. So you now need to describe the circuit. Let's start with the behavior. Assuming it starts in state 0, what happens? As long as you receive an input of 0, it will stay in state 0, and the output will be what? 0. We are describing the circuit. You couldn't describe it by looking at it. And then you are telling somebody it starts in, as long as a 1 comes, it moves to state 1. And then from then on, the output is the complement of the input. It will never leave state 1. But the output is always the complement. What circuit does that? So if you describe the behavior, this is what we are saying. That is a two's complementer. Two's complementer circuit. You've done those circuits. So that is analyzing a circuit. The procedure never changes. It remains the same. You identify the circuit, you derive the excitation equation and input equation, then derive the state equation, and then you go and determine from the equations, you derive the output table and the next state table. You combine them into a full state table and you draw the timing diagram. In the exam, you draw either one, timing diagram or state table, because they have the same information. So that is basically how you analyze a circuit. Now, from now on, we're just going to look at different examples, different flip-flops, but the procedure still remains the same. You always start with the most basic. Now, let's go to this one. Here you've got two variables. This is for flip-flop A, flip-flop B. So how many states will you have? You'll have 4 states. You should know that. There is your output. There is your input. There is your state variable A. There is your state variable B. Analyzing the circuit, you've been given a circuit diagram. Analysis, the question is, what does the circuit do? Or how does it behave? That is analysis. You want to answer that question. You cannot, just by looking at this figure, unless you have used it, know what it does. So analysis, you have to use equations and all that and determine what it does. How many states? There are 2 state variables, so you will have 4 states. You have to label them. Luckily, you've got them as A and B. We will skip some steps. So determine the flip-flop input and output equation. You have, can you determine them? I need you to give me what dA is, D for A, and D for B is, and what Y is as a function of X, A, and B. Can you go for it? I know you are alone. You can hang there, do nothing, but you will pay for it. Most of you are with me in digital systems. You saw how my section is. We are very much aware that you've got WhatsApp groups to exchange and do what. I'm very much aware. My multiple choice questions were from the question bank. You never did the same. There was randomness in the questions that come, randomness in the way the multiple choice are shuffled around. So that won't work. I'm aware of what goes there. You will not get a question that you can copy that says describe or list. Even explain, forget it. That is why my section, the part that wasn't very good, because it is more of a design part. Even if you get the same question, the parameter changes, you have your own question. We are aware there are WhatsApp groups on exam. You will not manage that way, I'm concerned. I dig deep in settings. So when I tell you that do this, you don't do it, we will start emails later at the end of the course. So attempt, I need DA, call it DA, get that, those equations, and then D, the second one, those input equations, and then I need Y. Got 2 minutes to give me that. Okay, if you have a question within 2 minutes, just ask. Okay, that's fine. Okay, those ones who have done DA, just go for the B. This is one course, if you participate, it's very straightforward. And it's got very few topics, and all of them will come in the exam. There will be a web forms question. There will be analysis synchronous. There will be each section has got a question. Okay, those ones who have done, thank you. We will see how it goes. I'm just giving time for the rest of the people to do it. If you are here and you cannot get D, A comes here, it goes there. X comes here, X comes here. This one is what? This one comes back here, that is B. So you've got B here, you've got X, you've got X, you've got A. If you can't give me what D is there, then I'm not sure what you are doing where you are. So just continue and get it. Okay, that's the guys who have got it. Let's wait and see. Yashil, I think you are right. Lindo Kudle also got the same. Umeshan got the same. So go to DB and Y. That is the first thing is label your inputs, your state variables, the outputs of your flip-flops and the output, first one. The second one, determine your equations. The equation is a model. A circuit can be represented by an equation. So determine the equation. Okay, DB, this one, yes, yeah. That one looks simple. Okay. Okay, Yashil, that is okay. Lebohang, right direction. Okay, people seem to have finished. So let's see what we have. Okay, remember, I've used the next step. I said, remember here I said some steps will be skipped. You know that D is a diff. For a D flip-flop, the next step will be D. So I've just removed D and gotten that. That is B, the next, that is Y. So you can check your solution. I've just dropped the many T's and just left it there. Anybody with a problem there? You can confirm once you do this, remember mathematics, you have converted from electronics to mathematics. You have modeled your system. You know what we call system models. You modeled your system. So now the table shouldn't be a problem. Since this is the beginning, okay, can you determine? So draw your state table. The present state, you've got A, B. Input, you've got X. Next state, you've got the next state of A, B. So this is AT plus 1. This is AT, BT, BT plus 1. The next state, and that is the output Y. Can you draw this table and fill it? Because it's the first one you are doing. I'm giving you 3 minutes. You just need to know how it is done. So draw the table. You've got the equations there. I want you to know where you get these combinations. It reaches a place people in the exam ask me, where did you get this combination? So by drawing and filling it in yourself, you will know where we get them from. We look for all the possible combinations. You can do it, but get used to doing it. Get involved in doing it. You probably don't need the whole table. You just need about 3 rows, but at least do them before we move so that you see where we are getting what and where. Okay, I'm giving you the 3 minutes. Okay, you should at least have gotten, you have your present state A, B, input X. You fill in the different combinations for all these 3. 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1. Use this configuration, 0, 0, 0, 1, 1, 1, like that. Now, this is the equation for the next state of A. So it is A X or Bx, Ax or Bx. So definitely it will be 0. You got that 0. B is A complement, is 0 complement, X is what? 0, so it will also be 0. Y is A or B, X complement. A or B is 0, so whatever happens is 0. Surely at this level, we shouldn't go and fill in those combinations. So you can do that. Anybody with a problem there? That is your state table. Now, this, I've just told you, different books have different orientations. You will find a book that writes a state table like this. You will find another book that says present state AB, next state for X equals to 0, X equals to 1, AB, that's the next state, and the output for X equals to 0, X equals to 1. Different things, same thing. So don't be shocked if you see different types of state tables, but they have the same information. Yes? Okay. The next state equations, I'm taking questions, and I actually feel good if people ask questions. How did we get these equations here? They are the same here. Okay. This is the circuit. From the circuit, you can capture it mathematically. So what did we do? We labeled our inputs, outputs, and state variables. Our state is A, of course, this is A complement, B complement, you've got Y, which is the output, you've got X. Yes, I'm just checking, yes. Okay, I will answer questions one by one. Oh, Sumedran, are you okay now? Okay, for the sake of the others, because I had started, let me go through. So now, from that, you get your output equation, the equation of Y in terms of X, A, and B. You get D here, dA in terms of the same input and present states, and dB. But because we say the next state for a D flip-flop is just what is at D, we didn't write D. We just, otherwise we were supposed to have written like this. We are supposed to have written AT plus 1 equals D, which equals that. So we've just removed D. And then instead of having T, we just left that T. And then we came and got this table. And we are saying that is a different orientation. Let me just take questions here. Okay. Sumendran, I hope you are okay. You've said you are. Okay, okay. Yeah. Different. This is the most widely used type. But there are some cases where this orientation is better. When you are optimizing row matching and doing things, when you want to check the relationship between this row and that row, this configuration tends to be better. But in most cases, we use that. Okay, I'm just taking questions for those who are asking. So now you've got the one who is making noise. Is it Lubo, please? Hello? Can you mute? Hello? Sumendran, the times in the equation is a times a multiplication is basically an AND gate there from the equation. Check properly. Okay, you are asking why is it 80 times what? Let me go back and see what you are asking here. I can't see where it is times T here. Is A is not times, this is not times T. This is A at a time T at the present state. This is A at a time T plus 1. The next state is not a multiplication. The T stands for A T here stands for current time. A at the current time, A at the next time, which is the next state, is not a multiplication. That's why here we even removed the T. At the current time, the values at the current time, this T means at time T, the current time. T plus 1 is the next time, next state, is not a multiplication. Thanks for asking. And don't even be afraid of asking. When you are writing the exam, you will be alone. Okay, now, after that, so that is our table. Now, from here, we won't waste time drawing a state diagram. The state diagram should look like that. And you can explain how your machine behaves. If it starts from here, if you receive a 0, it will stick there. If you receive a 1, it goes to that state. If you receive a 1, it goes there. If you receive a 1, it goes there. So if you receive a 1, it circles. So you can explain. There are some machines that you can't even explain. So the state diagram is that. The state diagram is derived from that. Now, that is the first way. There are two ways of analyzing these circuits. The one is using the characteristic, the equations, and then you make a table. The way we've been doing, you've got the equations and then you get a table, which is the easiest way that is used by almost everybody. The other one is using the characteristic equation. Each flip-flop has got an equation that relates its inputs to the next state. That is what we call a characteristic equation. For example, a D large, the next state, the equation for a D large is very simple. AT plus 1, the next A is just the same as what is at D. So if you get what is at D, you get the next state. So that is a D flip-flop. One with the neighbor has got its equation. Master slave has got its equation. T flip-flop. The next A is the present A, exclusive or T. No memorizing of these equations, they will always be given, but they are not given. Most people prefer using the other method. So let's look at this example. You've been told analyze the circuit with the D flip-flop. We want to use the characteristic equation. The characteristic equation of a D flip-flop is just the next AT plus 1 equals D. So if you've been given this is your circuit, just find out what is at D. Okay, this is A. So what is at D is A exclusive or is X exclusive or Y exclusive or A. That is what is at D. Substitute this here. Then you get AT plus 1 is A exclusive or that. Once you get that, then you have your table. You've got your equation. You can have your table. That is another way. After the table, then you can draw your state diagram. Note that this has got two inputs and it's got no output. It is not a must that you should have an output. You can have as many inputs as you want. If there are different combinations, you separate them with a comma. A slash separates the inputs to the output, but different types of inputs for two inputs, you separate different combinations with a comma. Those are the things that you should use. So that is how you use a characteristic equation. Any questions there? You've been given an equation of the way the next state of a D flip-flop as a function of the input. That is what you call a characteristic equation. So you just derive what is at the input and substitute it into that equation. It will become interesting when we look at the other circuits. I'm still insisting, we are done with the analysis. We're just looking at examples, different configurations, but the procedure still remains the same. Now, the D flip-flop is the easiest. Now, we are going to do the same thing with the JK flip-flops. And we have said there are two ways of solving it. One is the characteristic table. The second method is the characteristic equation. So The procedure for method A, using the table, you determine the flip-flop input equations in terms of present state and input variables. You go to the table, you list the binary values of each equation. Then from the table, you find the next state and fill it in. So that is our circuit. Can we just try and do it and confirm with me first? So you label the circuit. So you've got, this is A, you can call it, this is flip-flop A, this is flip-flop B. This is your input X. Okay, so you've got A, B. Okay, and then there is no output here. You've got the clock. So can you determine JA, KA, JB, KB in terms of X, A, and B? Let's go for that. Just try and do it on your own. And then when we advance, we'll be moving. So I'm giving you 3 minutes. It's simple. It doesn't have a lot of things to give me. JA, KA, JB, KB. Remember, the first step is label the circuit and determine the flip-flop input equations and output equation before we go to the state equation. So go for it. You've got 3 minutes to do that. If you have a question in between, you can send me a chat. Our 3 minutes start. Okay, I'm saying the answers. Okay. Eminently, you are okay on the right track. JA is fine. Scanyiso. Yeah, here you've got KA. Okay, you've got that. That is fine. Okay, Yashil, you are done. Okay, so people are done. So you should have gotten that. It's very straightforward. So you've got JA equals B. KA is equals B complement. JB equals X complement. KB equals A exclusive or X. You should have gotten those. Now, this is a bit more interesting and I want you to pay attention. These are the procedures, okay? There is someone, I'm just looking at answers, okay? Okay, those ones who got the answers, just confirm with what I have here. Okay, so most of you have it. Okay, now, I need you to pay attention properly here. Remember, we were using a D flip-flop. And with the D flip-flop, what is at D becomes the next state. That is not the same with the other flip-flops. They involve a lot. So just focus on this. Label the circuit and derive the flip-flop input equations. We labeled it. We derived the JA, JB, KA, KB. We've done that. Create a blank state table. Then fill in different combinations of present state and input. That is 3. You create a blank table, fill in all the combinations. Where do you get all the combinations? 0, 1, 0, 1, fill in for all that, all the combinations. You know what I'm talking about. Now, step 4. And if you don't understand any step where you are not getting what, just ask. This is one comprehensive example. Now, you are saying X can be 0, 1, 0, 1, 0, 1, B can be 0, 0, and what? So those are the different combinations of X's and Y's. We know where we get that. Now, step 4, we need to find JA, KA, JB, KB in terms of these combinations. So we are saying if A is 0, what is JA? JA is B. And on this row, what is B is 0. So we expect a 0 here. KA is BX complement. So B is already 0. So we expect a 0 there. So you fill in the green. Any problem there? We know where those, remember we had these combinations, and our circuit is the one that is giving us those logic. So we feel that. Any question? I'm pausing because I want you people to digest that. Where did we get that? We got it from the equations. We had all the combinations of the present state input. Now we are filling in the flip for A0, B0, X0. What is JA, KA, JB, KB? You get it from these equations. That is what we have done. Fill that, fill that, fill that. After that, we are done with the equations. Now we need the next state. Next state equation. Remember for a D, what is at the input cost? That one does not. So let's look at one combination. So now we are on 5. Equipped with the flip-flop inputs and present state. Now you've got this row and that row. You can now fill in the next state using the characteristic table. We call this a characteristic table. So let's look at one. If the present A at the time t is 0, okay, and remember J and JAKA is 0, 0. What will be the next state of A? Ask yourself that question. Remember, the present state is 0. The flip-flop inputs, flip-flop A are 0, 0. You come to this table, when J and K are 0, 0, there is no change. So if the present state is 0, what is the next state there? Somebody to answer that. Yes? Okay, it's on a chart. It is 0. That is good. And there's a lot of you that have said. We are just interpreting a table. So we have said, you got this from the equations for this combination. Now you are saying, if the present state, we are looking at flip-flop A, the present state is 0. J has a 0, K has a 0. How will the flip-flop behave? You come here, JK. When J is 0, K is 0, there is no change in the state at the output. So if it was 0, then it will remain 0. There will be no change. That is the 0 that you have. Okay. Let's look at E at B. How did we get that one? JAKA is 0. JBKB is 1, 0. The present state of flip-flop B is 0. What will be here? We have said 1. Where does it come? Come here, 1, 0. When JK is 1, 0, it doesn't matter the previous state. The next state will be 1. That is why we have that 1 there. You just check the chart. Okay. Let's look at another one. B. Let's look at there. The present state is 0. Okay, JBKB is 1, 1. What should you expect in that place at B? You go here 1, 1, it will be complemented. It was 0. So what do you expect? So you expect a 1. Thanks those ones who are answering. So that is how you fill in. It's a matter of using a table. Most people prefer this one. They don't like that. They don't like the characteristic equation. So I need questions on this. Ashlyn, those ones with delayed, I'm answering questions with delayed registrations. I've got the past 2 lectures. I've got the audios. I've got the lectures actually recorded, just like we were doing in digits. They are online. They are on Moodle. For these 2 lectures, they will be on Moodle after tomorrow. So you can catch up. You can catch up with the lecture rewind and all that. It's very easy to catch up. Okay, I'm answering questions for the people who are saying they only registered yesterday. So you can catch up. In fact, most people, when they upload recorded lectures, they just go for tutorials. They don't lecture again because it's going through it twice. But I prefer I go through it twice for people to understand and ask questions at real time. Anybody with a question on this? Anybody with a question on this? So once you do this, you've got your state table here. Remember, this is not part of the state table, the inputs, but they help you derive the next state. Then you've got your state table there. You can draw the state diagram. You have solved the procedure. You have solved the question using the table. There is another way we say the one of using the procedure B, using the characteristic equations. You derive the input equation, JA, KA, the same way. Here they are. You got this. And then this, the equation for a JK flip-flop, the characteristic equation says the next state of A or B is J A complement or plus K complement A. That is an equation. Don't memorize it. Where is it coming from? Where is that equation coming from? I just want to go back. That equation is coming from we saw that table there. The JK flip-flops, master slave, edge triggered, that equation you will be given. That is the equation that relates the J and A. It couldn't be B, C, or D. And that, we got that equation there. So that is where it is coming from. Okay, then after this, now that is, you substitute. For flip-flop A, this is JA. Its output is A. Okay, this is KA. JA is B. So here you will have B. KA is what? BX complement. Here you will have BX complement times A. For flip-flop B, you've got JB complement. JB, this is JB, which is X complement there, plus K for B, that is KB, which is that, times B, is the output. So if you do that, once you substitute, you will get that. You do that, you substitute, you will get that. And then you have your table with the combinations, and then you can get the next state from these equations. After you do that, you draw your state diagram. By now, you know why people don't like this. You're supposed to be engineers, but people don't like these additions and doing what they had rather interpreted the table, read the table instead of taking A complement and B or what. So they end up failing here and failing here. So most people don't like the equation. They prefer using the table. Any question? This is the procedure B. Okay, now, on your own, I told you analysis is basically the same. Can you just try and do that on your own? Now, as we speak. Just do it until the end. Here is the characteristic equation. You can use the table or the characteristic equation. When you finish, just talk to me. Okay, I would recommend, I'm answering questions as we go, and I really like it when you ask questions. I would recommend the table one, because with the characteristic equation, you might need to simplify the equations using a kind of map or, some other simplifications. And people don't like that. They end up failing. Okay, so most people, in fact, almost everybody uses a table. They don't like going into the mathematics of simplifying what and what, those equations, they don't like that. So most people use a table. And I don't fix students to use to use the characteristic equation. So I prefer you use the table, unless if the question specifies otherwise. I'm answering questions and I'm assuming the rest of you are doing this. Label your circuit. For you, it is labeled already. And don't worry about the reset and the clock. Even if you use them as inputs, you should get the right logics, but leave the reset and the clock. Okay, for those ones who need to be checked, TA, that should be simple. You've got X coming in, multiplied by what? B. That is for TA. TB should be what? Is X. So the equations here are very clear. Y is what? And you should tell me what kind of machine is that? Is it milli or more? There's always that question for 1 mark. I'm sorry, for this, Sahil, for this case, forget about the clock and reset. And it's a more circuit, you are right. It's only affected, the input does not go directly to the output. Thanks, Tokozani. So we've got that. The equations are simple. I just want you to just do it and finish. Instead of looking at what I've done, you will be satisfied then. So you've got the equations, create the table. It's a short one. You've got your A, B, and then X. Create that table. Just try and do it to completion. You will see how you will feel when we get right. Use the table first, and then on your own, you can use a characteristic equation. But in this case, maybe the characteristic equation could be short. But just do it to completion. Analysis is always straightforward. It's following procedure and doing it rightly. Most students get the question right. Okay, so we got those equations. You got those equations. Label the circuit and derive your flip-flop input equations. You did that. You created the blank state table. Remember, it reaches here, the output. So you've got your present state, you've got your input, not the order. Don't flip things around. And then you've got your next state. You've got your output and then flip-flop input. You can flip things around you and be right and fail. If a lecturer is marking, you guys are 120. Let me just pay attention to how things go wrong. I'm marking 120 scripts and it's 3 a.m. at night. And you put B here, you put X here, you put A here. And when you mark, you memorize, you put the template of the marking scheme in your head. So you are basically reading a template. I will not have time to go and interpret and look and do. I will spend the time that I would have marked 20 questions on your script. It does not work like that. So you find that somebody has failed, yet if you go in, you've done the right thing. And if you get a mark like 65, where you might not go and check your script, you will die with that fail, yet you passed. So stick to the norm. Start with the present state. You've got A, B, input X. Don't flip and put the input here and what. I don't have time to go through every bit and all that. Next state, output, the flip-flop. So you fill in this. You've got your equations, TA, TB, and Y. Then you just come like we said. If A is 0, the present A is 0, TA is 0. Are we together? What is at the next state? You come here. If it is 0, there is no change, so it will be 0. Wait, it will be 0 here. A is 0, TA is 0 here, still 0. A is 0, TA is 0 here, 0. Okay, A is 0, TA is 1. If TA is 1, it toggles, so it will toggle, you get 1. So you should have filled that for A and B using those. And then your table is here. In the exam, don't struggle and remove this and draw another table. No, we're not examining you on how to draw. Once you reach here, you know this, the state table consists of that, and that. Just leave it. Any question there? Okay, characteristic, there are two ways of doing that. Our equations still remain the same. You take that and substitute here. For each of them, you've got the A and B. Once you do that, you get that A, and for B, you get that. Then from that, you can create your table and fill in your values. That is procedure B. And then that is your circuit. You need to describe the circuit, by the way. If you check carefully, once you find that that circuit, when X is 1, it goes around. Yes, no, Kolo?
So I'm confused with the example 5. Like you said, TA is affected by A, but the input at TA is BX. So can you just go back to that one?
Okay. I'm going back. Let me just click there. Where, on this slide or the previous one?
The previous one.
This one that I am in, or the previous?
The previous one.
Okay.
This one.
TA is what?
It's BX.
Yes. So what you do is, probably I skipped that step. You have your ABX, you have filled them in. So these values of TA and TB, you will get them from A, B, and X. For example, what is TA? TA is BX. So to get that value, you will come here is B, 0 by 0, you get it what? 0.
Okay.
Are you getting that? These values, yes, you get them from this equation. Let me look for another one. Okay, let me look here. TA here is 1, B is 1, X is 1, so TA is what? 1.
Okay.
After that, I probably skipped that. I just said you find your TA from these values. Then after that, that is when you go to the next state. Remember, we are fighting to get the next state. It's the one we don't know. For the present state and inputs, we use all known combinations. The equations will give us the flip-flop inputs, and then from them you can get the next.
So we start with our TA and our TB, and then we do the next state.
We start with, you start with all the combinations of this. This is, you get everything, all the combinations of A, B, X, the present state. And then you get TA from the mathematics, from the circuit, using these combinations. Then you are done with the circuit. And now you look at the behavior of the flip-flop to give you the next states.
Okay.
Yes. Yashil? Yashil? Why is A B? Why is it that when A and B are 1, 1, Y is 0?
I understand now. I was looking at the next state A and B when I was supposed to look at the present state.
Okay. By the way, don't even feel bad. It's good you make a mistake now. I like somebody who checks, because then it means you are going through. It's good you do that now. Analysis procedure.
The output Y in this case, you can fill in straight away because you already have A and B.
Yes.
You can fill in out Y straight away and then T.
Yeah, Y does not come from this.
Yeah.
Why? You look at that. You've got Y is A and B. So you just look A 0, 0, it will be 0, 0, 0, 0, 0, 0, 1. I can't see what is it. Oh, 1, 1, 1. You are using these equations, are interpreting, they are modeling your gates, your AND gates, and what in the present state. That is where you get that for all the combinations of that. Taking questions, it's good if you ask questions. It means we are understanding. So this is what we are saying. You also, the aim is to get the state table, state diagram, and tell somebody what the circuit is doing. Who can tell me what the circuit is doing? Obviously, the reason why people like a state diagram, it's easier. This and this have the same information, but this is better. Pictorially, you can see how the circuit is behaving. Who can tell me how the circuit is behaving? It keeps on counting from 0, 1, 2, 3, 0, 1, 2, 3, when the input is 1. When the input is 0, it does not advance to the next stage. And the output will be 1 only and only if the present state is 1, 1. You have described the circuit. You can see it's very clear from the diagram how the circuit is behaving. There are some, though, you can't describe. It is a counter with the sequence 0, 0, 0, 1, 1, 0, 1, 1. You are used to designing counters. You found somebody has designed a counter you didn't know, but through analysis, you can tell that person the circuit you designed is a counter when the input is 1. When the input is 0, it doesn't, it stops. And the output will be 1 only when you are in state 1, 1. So that is the description of the circuit. Eventually, the aim is to describe. I'm taking questions. So, in conclusion, anyway, analysis never changes. Those steps will always remain. You can use the table or the characteristic equation. The table is easier. You will be given the table. So, basically, in the analysis, you are given a circuit diagram. You have to look for your flip-flop input equation at the input and your output equation. Then, using those, you can look at the behavior of the flip-flops using a characteristic equation or a table that will give you a state table. Then you can reduce. We haven't done reduction. There are techniques of reducing state tables. That's another chapter. And then you can have a state table or a state diagram and you can describe your circuit. So that is what we've been doing today. I'm taking Lindo Kudle. Minedle, you are right. When the circuit is 1, it counts. When it is 0, it stops counting. Lindo Kudle, you are saying, how do we get the values of A and B for the next state? I will repeat that. You are asking how do we get the values of A and B using which method? Lindo, you need to tell me the method you want me to explain. Do you want me to explain the characteristic equation? We are using 2 methods. Do you want me to use the table or the characteristic equation? Lindo Kudle, Yaka. Okay, you are saying table. You know where these equations come from. Let me just go back and from here, the first step is label your inputs, outputs, and state variables. That is our input, that is our output, these are our state variables. Step number 2, determine the flip-flop input equations and output equation. The flip-flop input will be TA, TB, output will be Y. That is as a function of X, A, and B. So those are the equations. Now, we've done that. We create a blank table. Then we fill in all the combinations of A, B, and X. Minendle, yes, you will be asked how the circuit behaves. Okay, so now you've got all the 0, 1, all the combinations of A, B, and X. Your question is, where do we get the next state? Now, from this A, B, and X, using these equations, you will get Y, you will get TA, you will get TB. From you have used the equations, you get this. The output and flip-flop inputs. Now, just pay attention to one. Let's pick which one? Let's pick a different one. I just want a different one where we have like one here. Okay, and then we have one here, and then we have a 0 here. Let's look at the next A. The next F will be influenced by what is at TA. Now, if the present A is 0, TA is 1, what will be the next A? We see when T is 1, it toggles, it complements. Okay, there was a 0. So if it complements, you will find a 1 there. 0 toggles to 1. How did you know that? You looked at the value at TA, and this table told you that how will the flip-flop behave? When T is 1, the next state will be a complement of the present one. That is why you've got a 1 there. Yes? Okay. Lindo, you are okay. I'm taking questions. Our time is now the question time. That is all what the analysis entails. What will change in the test, in the exam, is the circuit that comes. Otherwise, everything is the same. The circuit. It could be a JK and a flip-flop, a combination of many things. Otherwise, the procedures of analyzing sequential circuit is just that. It never changes. Okay, our time is almost up. That was a full lecture. Now, the next thing is the TAT. It is already on Moodle that you need. Yeah, the TAT is uploaded on Moodle. Whoever is asking, it's on Moodle. So that is a circuit that you need to analyze. The procedure, the same, label, get the inputs. This D flip-flops is easy. There is another one, JK. Same procedure, you identify it. There is another one with T. So just go and practice those 3. And then we will look at them in the TAT. We won't have much on Monday in the TAT. And then we'll be done with analysis. Any question or any comment? Hello? Any question or any comment? Okay, if there is no comment, then we will have to stop there. If you have anything, you will let me know on email. But go and do the TAT. We will discuss it on Monday. Make sure. No colo. Yes? I'm seeing a raised hand. Mdunge. Oh, she's probably forgotten. Yes, Monday is a TAT session. Go and do this TAT. We will discuss on Monday. From then, the following period will be design. Design is bad. You just have to attend. Design is more of creative. And where there is design, there is no copying. You should know that. So you just have to be there. Okay, if there is nothing, let me just check the chat. Okay, it's the same. It's Monday at TAT session. Yes. If there is nothing, thanks very much. Make sure you sign the register.